Good morning, everyone. Thank you for coming to this session. This session is about a product enhancement which we did for one of our products. It's basically syslog over TLS in BusyBox. So it came from an actual product need, like a customer wanted to have the secure logging for syslog. And from there, we built this feature around. And today, I would like to walk you through about this product feature. So generally, routers already generate a lot of operational data, which goes in plain text during the transit, and the customer needs sometimes, it has to go through the secure logging framework, and they want some kind of an encryption to be there while the data is in transit. And the feature is built on that aspect completely. We have three constraints. One is the embedded constraint, that the footprint of the feature should be small. We do have a minimal change constraint, that it should not impact too much code base currently existing on the platform, as well as we want to prove that it actually runs in a target platform. So this talk will show you all those things which we did for this feature. So this is about me. I have master's degree in informatics and electronics. I have some experience in software engineering. I do have, my first job is in Hughes Software Systems, and I have worked across industries like Microsoft, Amazon, Cisco. Currently, I'm an embedded systems engineer in Ericsson Software Technology. And I worked in the embedded router framework domain, and which develops components for wireless WAN and 5G router space. And this work basically come from practical need, where we need to secure the remote syslog without losing the lightweight BusyBox protocol. So this is the summary slide which we prepared. So the need is the router logs needs to travel in clear text, not in clear text. The customer expected then RFC style secure logging, and we need to preserve the BusyBox logging mechanism, logging footprint, lightweight footprint. So what we delivered is an OpenSSL backed TLS remote logging. The reason we choose OpenSSL is because the device in which we are developing this solution has already the OpenSSL library present in the device. In case OpenSSL is not present in an embedded device, there are other variants like Embed TLS. Currently, the BusyBox inbuilt TLS framework can also be used to support the backend. We added an optional public key pinning, like you can pin the server, remote server, to your BusyBox client. And we preserved the existing UDP logging framework path. And now we are planning to upstream this feature so that everyone in the BusyBox community can use it. So we have prepared small thing why it needed, and every change which we did is a gated TLS opt-in path. So existing behavior does not have any impact. You can opt in from the config, from the runtime build environment, whether you want the TLS to be part of your embedded system or not. And this keeps the entire development optional if somebody wants to take it, the path. So, so the existing path is the standard logging path, which is a UDP based. We observed a gap that remote logs were sent without encryption. The customer requirement was to have a secure logging path. And then we took the decision to build the OpenSSL backed TLS. And we added the public key pinning also, so that the server can, if some customer wants to pin the server, he can pin the server. So this is the end-to-end architecture, which I will showcase. So on the left-hand side, we have an Ericsson-based 5G router, which will act as a TLS client. and then the TLS handshake will complete with the remote server. For a testing purpose, we took the TLS server as a syslog-ng server. And then after the handshake completes, I will showcase you how the application data get encrypted, and we will showcase via a Wireshark that the application data is actually encrypted after the transmission. So these are the code changes which we did to support this additional path, preserving the UDP forwarding path. We introduced build flags, runtime path. There is a new TLS helper module which get introduced to implement this functionality. We kept the generic syslogd for the regular things, and we built a hook for the new TLS framework path so that the TLS functionality can be separated out from the existing code. Then we added the public key pinning, and we did the validation of the entire feature set. So this is the code footprint where we have total 6 files changed, somewhere close to 500 plus insertions done. 2 new files got added, and we added the TLS optional remote path and the optional public key check. So in the build framework, we have the make files, config files, feature gates, and the TLS flags. In the runtime path, we have the syslogd to maintain the options, the TLS state, the retry logic, the send loop. The helper module has all the TLS functionality like the connect, handshake, write, and cleanup. And then the API part is in a tls.h header file, which has the error codes and the helper interface. So we build, the build time integration is controlled through the kconfig in BusyBox. And we have a specific feature flag to enable the entire functionality if somebody wants to. And then we have the C flags to include the OpenSSL library includes, and the library paths to include the actual libraries needed to run the end-to-end setup. Pinning depends on, so we have created a dependency logic. The remote logging is dependent, the TLS feature is dependent on remote logging, and the pinning is dependent on TLS. So if somebody wants to enable the entire feature, he has to keep all the dependencies in place. Then we have added the build flags. All the TLS include path is in those build flags. Every code which we change is runtime controlled, compile time controlled in those build flags. And then we link with the TLS libraries present currently in the system, the libSSL and libcrypto, and we exported those libraries in our make files. And similarly, if somebody didn't choose the TLS new path, the by default selection will be the UDP path. So it preserves the old UDP functionality. This is the user interfacing behavior. So existing path is completely preserved, the UDP path in which you can give a -r option for the host and the port. Default port is 514. If it uses the UDP socket, no TLS state, nothing mentioned. If you take the TLS remote path, you just extend the host configuration from the default port to the 6514 port and give a -d option to enable the TLS path. It enables the TLS TCP session. It enables the complete client path. For the pinning, there is a separate option in which you can specify the public key pin file path. The public key pin has to be there in the embedded device present. And how it works, it compares the public key which you provided as part of the configuration with the public key received in the certificate. And if it matches, it continues. If it doesn't matches, it failed there with a mismatch. And this is the sample command which we showcase, like how you use the new path. Existing path will follow the previous semantics, no change, nothing. The new path will follow this semantics. And the design intent over here is everything is explicitly opt-in. No change in the current existing UDP behavior. That remains unchanged. This is the runtime state structure, remote host structure, which get extended. So we added the TLS things which we need to. For example, the TLS enabled flag, the context, the SSL context, as well as some things which we need for the public key, as well as to track whether we are doing exponential retry if the TLS server is not reachable during any time. So the session state is maintained using remote FD, SSL context, and the TCP TLS session. The pinning config is maintained using the public key pinned file descriptor, and the retry mechanism is maintained using the consecutive failures, and it controls unnecessary retries if the server is not reachable. This is the complete TLS connection establishment flow. So it starts with DNS lookup, where the host is resolved. Then we open the TCP socket. We already have an existing functionality in our BusyBox to bind the source IP if needed. And then it creates the TLS client context, complete the TLS handshake. There is a timeout of 10 seconds if the handshake is controlled by that timeout. Then we have the pinning, public key pinning option if it is enabled. And then once the handshake is completed, it enters in the send loop configuration. So on failure, we close all the resources, clear all the cache addresses, and increment the failure counters preserved in the code. And on success, we use the complete end-to-end TLS descriptors maintained for the session. This is the new TLS helper module, which was developed during this time. And this module basically supports mainly 3 set of functionalities. It has functions to open the TCP client socket, support the existing source IP bounding if the option has been provided while spawning the syslog, and uses a non-blocking connect and applies the connect timeout. The init SSL functionality is to initialize all the SSL related context, attaches the socket FD which was created by open connection, and then drives everything with the poll commands. And it enforces that the handshake timeout is preserved during this time as well. Then for the send and cleanup, we have developed small wrapper functions, which basically uses internally the OpenSSL APIs. So the OpenSSL APIs are wrapped inside these functions in all. So if somewhere I have to change the backend from an say OpenSSL to an embed TLS or an inbuilt BusyBox TLS, this file just needs to be changed. And this also maintains the TLS state, which gets preserved during the closure, as well as if we want to free the context and clear out the resources, it will take care from that. The main design consideration during this time is syslog. We want to keep it for logging policy and routing. And the TLS mechanics are all isolated in this new files. This is the public key pinning flow. So we load the pin when the -c option has been provided to the syslog daemon. It reads the peer certificate, which was received during the TLS session. It extracts the key from the certificate using the X509 API, and then it compares the key using another API. On match, it allows the encryption to proceed. On a mismatch, it clears out the entire context. The important point to note over here is we are not doing the complete full CA validation. It's just one public key pinning where we just ensure that if the customer enables it, it connects to the correct remote server in which it wants to send the logs. But it does not do any hostname, expiry, or any revocation validation. It's a small subset of the functionality which gets implemented. This is the message forwarding path. So we have the existing path, which is untouched. Whatever is currently supported by upstream has been completely preserved. The new TLS path has been implemented. If somebody opt in for this, this path will be used to send the messages using an encrypted format. So, we use the OpenSSL TLS client method, so it can negotiate with the remote server what kind of TLS support they are providing. If it is TLS 1.2, it uses the TLS 1.2 messaging framework. If it is TLS 1.3, it uses the TLS 1.3 framework. Now, this is the TLS server might be slow, might be down for some time. So this is how we handle the reconnect and the backoff behavior. If the TLS server is down, if the TLS server is slow, if the TLS server is misconfigured, the code ensures that we are not pumping too much traffic to that server, trying again and again, making the embedded device slower. So there is an exponential backoff algorithm has been implemented using the retry mechanism, and every time if it is not reachable, the retry has been twice the previous one, and it is bounded to maximum limit of 25 minutes. And it is controlled using these two variables mentioned over here. The remote delivery is always the best effort. If the remote server is available, we will deliver to the remote server. If it is not available, we won't be able to deliver. So no change in the existing BusyBox mechanism to do the syslog delivery to the remote. This is about the failure handling and cleanup. So we have different failure points like DNS address lookup failure, TCP connect failure, TCP TLS context creation failure, handshake timeout, pinned key mismatch, TLS write failure. So for all these things, we ensure that proper cleanup is being done. We shut down the TLS session. We shut free all the SSL session context resources. We closes the FD. We set the remote file descriptor to a negative value and clear all the cache addresses which we present in the system. And it checks everything, like we do not have any stale connections. We do not have any unnecessary retry loops, and we ensure that there is no resource leak during this entire process. And the complete cleanup order ensures that TLS shutdown happened completely before any socket closures. So these are the few review considerations which we did after we implemented this entire feature. From the security point of view, we ensured that pinning and CA validation has been thought of completely. What we can do in pinning, what we can't do in certificate validation, that has been completely thought of. Currently, we have, in the pinning, we provide only one public key file to the syslogd daemon. If the public key file at the server changes, there has been thought how can we implement that feature. So it's already thought during the review that we might need to implement a dual pin rotation window in which we can change the server without bringing down the syslogd daemon running on an embedded device. Then we thought about the TLS version which we supported, as well as the cipher policies. On the footprint side, we ensured that the existing system, whatever dependencies we have in the current system, we can live with those dependencies. We are not increasing the footprint by a larger value. We ensure that there is no impact on the memory and the RSS after enabling these features, and we have taken overnight runs to ensure that there is no resource overhead during this entire implementation. And we have the TLS stack options to enable and disable it. Runtime, we have the timeouts and the backup. We have the proper handling of the server down behavior. If the server comes up, goes down, it has been properly handled in the code. And we have the remote message log semantics also noted down during this. For the compliance part, we have thought about how we can ensure that the system which we are proposing is compliant to the FIPS if needed, as well as the crypto policies, whatever we support in the system. In the compatibility, we ensured that the UDP logging is preserved throughout without any breakage, and all the TLS is compiled in, even if, and if we don't want that feature to be enabled, then the runtime options are available during that part. And during the evidences, I will showcase the packet captures, the receipt logs, as well as the negative pinning and the server read down tests. So we have a recorded demo. So we will start with the syslog-ng server, which is listening on the port, TCP port 6514. We will start the BusyBox with this syslogd options, and then we will send logs to the remote server, and we will verify its encrypted delivery as well as the server receipt. So this is the flow which will happen. The client will be an E3000 5G router. It will first handshake with the remote server, which is basically a syslog-ng server running remotely. It will do the complete handshake, do the key exchange, and then have the secure path enabled between the client and the server. So this is the complete setup which we will do. I just mentioned the IPs so that we can take a note of these IPs during the Wireshark logging, so that we ensure that the client and the server, we can manage those things. And client is this, the E3000 router, which I already talked about. The server is the syslog-ng host. The transport is TCP TLS. And the port which we use is the 6514, the default port for TLS. So we start with setting up the syslog-ng server. We have the configuration file in which we enable the TLS IP port and the TLS configuration. Everything is created using the cert key, and we exported the public PIN key path. So we generated a self-signed certificate and a private key, extract the public key used for public key pinning, and then update the configuration file and attach all the TLS asset to that configuration file. So by asset, I mean the cert key file, the private key file, and the public key file. And then we ensure that when we started the syslog-ng server, it is listening on the port in which we want to, and we ensure that we ensure that the port is in the listen state as well. So with the E3000 router, we ensure that the compiled build contained the updated BusyBox code with TLS enabled in a compiled and runtime environment. And we ensure that the complete boot up sequence for that router is through. There is no errors observed during the boot up with that new BusyBox in place. And we also checked that the WAN interface is up and running so that I can reach from this IP to the remote server port. To enable the TLS logging, once my router is started, I separated out that daemon. I purposefully not started the daemon by default and have the flexibility to start the daemon once my system is up, so that I can give whatever option I want to. I can do it with -D option, -C option, or the standard remote UDP path. And once the daemon is up, I try to send a message. So log message is a CLI utility which we have in our router to send a remote message just for a logging purpose. So it will just generate that log with the test log 1 message. And then Below snapshot is the syslog-ng server that it receives the message testlog1 which has been sent from the router. Then we just showcase an example of public key pinning. Here I have the public key file presented in the router. It has been either while building you can provide the public key file, or once your router is up you can just copy paste the public key file in PEM file. And then while spawning the syslogd here with the -d option, I provided the -c option along with the public key pin file. And now, because the server is also having the same key, it will connect to that server. If I change it to another server, it will deny that connection. So now my client can only connect to a specific server given that key. Here again, we tried to send another log message from the router to the server, and we ensured that the server receives the message. This is the Wireshark capture proof, in which it showcases the handshake mechanism started with the client message hello. The syslog-ng has been configured to use the TLS 1.3. So you will see the protocol as TLS 1.3 during the entire handshake and the cipher exchange process. And then the data which is being sent, which is being highlighted in blue, is completely encrypted from the remote router device to the server. The capture has been taken at the server side so that we can manage easily and see the Wireshark thing. So this is the validation matrix which we prepared. So we preserved the baseline compatibility. The existing UDP logging is preserved with TLS disabled. The existing UDP logging is working even if TLS is compiled but unused, as well as we did the current BusyBox supports connecting to multiple remote hosts. So that functionality is also preserved during this entire development. The TLS behavior is TLS TCP without pinning, with pinning, with a valid public key. If the key mismatch or the pin fails, it handles the things properly. And then the TLS version and cipher mismatch. Reliability-wise, if the server is down, if there is any DNS failure, those cases are handled properly in the code. If the server restarted in between, that has also been handled using the backup mechanisms. And we have also tested, like if somebody wants to send me the burst message or the large message, those messages are properly handled as per the TLS TCP protocol. And then we got the overnight runs monitoring the RSS and the FD usage. So this is the takeaway. So we already implemented the secure logging to the existing BusyBox syslogd path while preserving the existing behavior. And everything is opt-in and the best effort syslog semantics delivery mechanism. And this work is product validated. We are currently using this feature in our product. Customers are using it without any issues. Going to the next steps, we want to refine this to an upstream friendly BusyBox contribution. So we plan to complete these items like generating the BusyBox config using the standard kconfig, as well as the build integration. We want to ensure that the framing which we did for the RFC handling is clear, that we only handle the best effort delivery scenarios and remote negotiation scenarios during that message deliveries. We want to ensure that the TLS versions which we support and the cipher policy which we support are crystal clear during this entire upstream process. And then we want to provide the dependency footprint, like what is the dependency with OpenSSL as of now. If somebody wants to change to embed TLS or inbuilt BusyBox TLS, those options are also available. Public key pinning is currently present. What is the plan for the public key rotation if somebody wants to? And then we want to provide all the maintainer ready test evidence, including the negative test as well as the long run test. And the code base is, it's the entire code base is already present in the Nordics site with that BusyBox repo link. And you can contact me if you have any things. And I'm open to questions, if any. Okay. Yes, please. Okay, so we uses the syslog-ng server, and syslog-ng server, when you configure, you specify the protocol and everything. And if, say, you receive the message coming from a remote device and it's get properly decoded in the server logs, that validates that the TLS part is completed correctly. So we can use any syslog servers like rsyslog, syslog-ng, or any property, and we can ensure that both the ends are seeing the same message which is transmitted from the client to the server. If there is any issues with the cipher handling or the TLS version, the message decryption will fail over there. Yes, please.
How does the whole architecture compare with like just using rsyslog? Is that an option?
It's an option, but then the rsyslog have two problems which we evaluated during our evaluation phase. The first option is you have to take down the entire rsyslog stack to the embedded device, which can increase the footprint by a large value. And the second is you have to maintain that also. So there is a maintainability issue which you have to ensure that, and whenever rsyslog updates their version, you have to pull down, maintain, ensure that if you have done some changes which are not upstreamed, you have to do those changes manually in the code, again release your software. So those dependencies we thought we can avoid by using the existing OpenSSL thing which is already available in our device. If some device does not have an OpenSSL, instead of rsyslog, the recommendation will be use embedded TLS versions like embed TLS or an inbuilt BusyBox TLS, because this year BusyBox TLS has also been improved a lot, and now it has good amount of functionality to support TLS going forward. Yeah. Yes, please.
Caching and like logs when the server isn't available. How does that?
So the delivery is best effort. It means in the existing also, if the UDP server is not available, the logs get truncated. So the same thing will happen over here. So if the device is generating, say, 10,000 logs and the server is not available, every log will get truncated. You will not receive the log anytime future. There is no cache for that log, nothing. Okay. Thank you everyone for joining. Thanks a lot.